Hi everyone, welcome back. In the last section, we trained a ResNet classifier. We gave it a satellite image and it predicted a single level, such as cropland or forest, for the entire image. That's image classification, one level for the whole image. In remote sensing, traditional methods such as random forest can also classify satellite imagery. Today, we will use a deep learning approach to do the same thing. Instead of predicting one level for the entire image, our model will predict a class for every single pixel. This is called semantic segmentation. It allows us to generate detailed land cover maps that can be opened in QGIS or other GIS software for further analysis. So let's get started. Why segmentation? Look at these two outputs. They came from the same Sentinel-2 tile, but they tell us very different things. One on the left, our ResNet predicts a single level, agricultural. One prediction for the entire image tile. Now look at the image on the right. You can see a river, a road, a small settlement. The classifier misses all of those details because it produces only one prediction for the entire image. With a semantic segmentation, every pixel receives its own class, instead of a single level for the whole image. We obtain a classifier raster that preserves the spatial patterns in the scene. So remember, image classification in computer vision, one level for the entire image, while semantic segmentation, one level for every pixel. It is a simple difference in concept, but it completely changes the level of details and the types of analysis you can perform with the output. So what does the output actually look like? It is called a segmentation mask, and it is simpler than it sounds. It is just a 2D array, same height and width as your input. Each cell holds a number, an integer. 0 means water, 1 means forest, 2 means urban, and so on. When you color code that array, you get a land cover map. That is it. And in the notebook, if you print the mask, you will see something like this. Shape 64 by 64, data type integer 64, unique values 0, 1, 2, 3, and 4. These are your class indices. This is what our unit will learn to produce. Now, what data are we using? We are using the Eurosat dataset. It is built from Sentinel-2 satellite images and contains 10 land use land cover classes from locations across Europe. The dataset includes about 27,000 image tiles, each measuring 64 by 64 pixels. We have already downloaded and unzipped it for this course. The classes include forest, river, cropland, residential areas, industrial zones, highways, and sea or lake. Now, I want to be honest with you. Eurosat was originally designed for image classification, meaning each tile has a single class level. For this tutorial, we used that image level to create a simple segmentation target by assigning the same class to every pixel in the tile. This is useful for learning how semantic segmentation methods work, but it's not true pixel level segmentation dataset. In real-world segmentation projects, You would use datasets with a manually annotated pixel level masks, where every pixel has its own ground truth class. Before we build anything, we need to talk about how we measure model performance. I want to start with what not to rely on, pixel accuracy. Here is why. Imagine that 90% of an image is forest. If a model predicts forest for every pixel, it achieves 90% pixel accuracy. But the prediction is still poor because it completely misses the river, the road, and every other land cover class. That's why semantic segmentation commonly uses intersection over union, IOU. For each class, we calculate the number of pixels where the prediction and the ground truth overlap. This is called the intersection. We then divide that by the total number of pixels that belong to that class in either the prediction or the ground truth. This is called the union. An IOU of 1 means a perfect prediction, while an IOU of 0 means there is no overlap at all. We calculate IOU for each class separately and then average the results. This gives us mean intersection over union. Throughout this course will be our primary metrics for evaluating segmentation performance because it measures how well the predicted regions match the ground truth regions for each class.